Hi everyone, welcome to the last video of our series, A Beginner's Guide to Hardware Software Co-Design. Building a Linux-controlled hardware accelerator on the Zinc UltraScale Plus SoC. In the previous videos of this series, we designed and implemented our custom half-adder IP in Vivado. Then we verified that our hardware works correctly using a simple bare metal application in Vitis. So why an operating system? Bare metal is great for simple tests, but an OS gives us immense power. It offers a sophisticated set of features such as file systems, networking stacks, multitasking, user management, and vast software libraries. So the goal is to create a complete bootable Linux system tailored specifically for our hardware. PetaLinux is AMD's official embedded Linux system development kit, or SDK. It's built on top of the Yocto project, the industry standard for creating custom Linux distributions. And it automates the incredibly complex process of building a full Linux system. It integrates the bootloader, U-boot in this case, the Linux kernel, and the root file system, which contains all the applications and libraries. In particular, it reads our hardware definition XSA file from Vivado to start the configuration. The path to creating a bootable image begins with setting up the environment. In fact, we'll work inside our Azure Linux virtual machine where the PetaLinux Tools are installed. Then we'll create a new PetaLinux project, pointing it to the XSA file we created previously. Subsequently, we'll explore the PetaLinux configuration menus to see how we can customize the kernel and the root file system. Afterwards, we'll build the image by running the PetaLinux build command. This will take a while as it downloads and compiles hundreds of software packages. And this is the main reason why we'll be using a virtual machine, because of the multiple cores that we'll be able to use in the cloud in comparison to the lower amount of processor cores available in our own computers. And finally, we'll package the output into a bootable SD card image and write it to our micro SD card. By the end of this video, you'll have a micro SD card loaded with a fully functional custom-built Linux operating system that includes your own application. You'll be able to boot your AUP ZU3 board into a Linux command prompt. You'll have a complete end-to-end working system where you can type a command in the Linux terminal and watch your C application control your custom FPGA hardware in real time. In the end, you'll have successfully completed a full hardware software co-design project. So let's start setting up our Azure virtual machine. From the Azure home view, let's click Create a Resource. Then let's click Create a Virtual Machine. Select your subscription and let's hit Create New. As a name, we'll click Co-Design and hit OK. We'll call the virtual machine PetaLinux. We'll leave the default settings except for the virtual machine image, which we're going to select Ubuntu Server 22.04 LTS. And this is because of the compatibility with our PetaLinux version. Then we can select the virtual machine size. In this case, we'll see all sizes and we'll choose the largest one of the B series, so B20 MS. The B20 MS virtual machine size will allow us to concurrently run 20 virtual CPUs with 80 gigabytes of RAM. This will allow us to better see how PetaLinux and Yocto parallelize the multiple tasks throughout the build process. So we hit select, scroll down, we'll generate a new SSH key pair by leaving the default settings in this case. Remember, we need the SSH port to be open in inbound direction. We hit next disks. In this case, we'll view the recommendations to see what Azure suggests. And on the right panel, we can see we have several recommendations. One changes the virtual machine size that goes from B20MS to EC20AS. If we choose alternative recommendations for the same region, we'll see the E20S v3. And if we choose alternative recommendations for the same size, we'll see that the region has changed to East US 2. For simplicity, we'll be clicking on this one, East US 2, and adopt a suggestion. At this point, we'll just continue by clicking next disks. The default image, as indicated in our guide to Linux hardware, should be of at least 100 gigabytes. Therefore, we'll choose a 256 gigabyte OS disk size. Then we hit next networking. We'll leave the default settings and verify that SSH has been selected from this list. And hit next management. Here we'll leave the default settings and click next monitoring. Similarly, we'll leave the default settings, the next advanced. We won't need to be creating or setting up specific features, so let's hit next tags. And to finish, we'll just click review and create. At the top, we'll see the price for the virtual machine size and the rate per hour. We'll also have this alert or warning that the SSH port is open to the internet, but this won't matter since we'll be using this virtual machine for a brief period of time. And then we have a summary of the settings we previously established. So we hit create. We'll download the private key and create the resource. Once the deployment process finishes, we can click Go to Resource and connect to our virtual machine. And then we'll select Native SSH. We'll just copy the Azure user we can see here and navigate to the folder in which we downloaded our PEM SSH key file. We'll right click on the folder and hit open in terminal, and then type SSH -i, and here we can see PetaLinux key.pem and paste the user ID and the virtual machine's IP address. We hit enter. and we're in. At this point, we can follow the guide I published a few weeks ago. A guide to Linux hardware software co-design on the Zinc UltraScale Plus SoC. You can find this guide through Google or in ResearchGate. So if you navigate to page 25, you'll see a set of commands that we need to execute in order to get this virtual machine up and running. So we'll start by updating the software packages already available in the virtual machine. We'll hit enter when we see which services should be restarted. Then we'll install some libraries that are necessary for PetaLinux to run. We got a couple of messages indicating that the command wasn't found, and this is due to the fact that in the PDF the sudo apt install command is 3 lines long and it executed each line as a separate command. So we basically just have to copy this text and paste it to the command line, and this second line, and then the last fragment. And hit enter. Then we create the PetaLinux folder. Another tool we'll be using for simplicity is Win Secure Copy, or Win SCP, which is free. You can download it from winscp.net. Since the installation is straightforward, we'll skip it for now. So we'll open WinSCP. Then we're going to create a new site. We'll copy through SCP or secure copy. The host name is the virtual machine's IP address. And rather than typing in a username and password, we'll click Advanced. Then go to SSH Authentication and browse for the private key file we just downloaded, the PEM file. Since we can see it in the folder, we'll select all private key files and it will appear. At this point, it will ask us if we want to convert it to a PuTTY format, so we'll click OK and save it to the same folder. OK again, and then OK, and log in or save. OK, and log in. We'll accept. The username is Azure user. Hit OK. And we're inside our virtual machine. So following the guide, we have to copy the PetaLinux file, PetaLinux installer. Within AMD's PetaLinux downloads page, we'll click the version 2024.1, which is the one compatible with the board's manufacturer's files. So we'll look for the PetaLinux Tools installer, full product installation, and we'll download it. And then we'll click download. When PetaLinux finishes downloading, we can drag it and drop it into Win Secure Copy. As we can see, the PetaLinux installer has been copied to the virtual machine. We can verify that by listing all the files in the virtual machine, and we can see the installer. Now let's make the installer executable. And let's run it. We'll hit enter. Then we'll type the colon and Q. We'll accept the license agreement by typing Y and hitting enter. Similarly, we'll type colon Q, Y, enter. And then we have our target. So we'll type home, Azure user, then PetaLinux, which is the folder we just created. When the PetaLinux SDK has been installed, we can load the toolset into our terminal by executing source PetaLinux settings.shell. Then we'll create the project folder and open it. Then we need to copy the platform XSA file and the PetaLinux base 8 GB board support package to the project folder. So we'll start with the XSA file, which is in the Vivado folder, co-design Vivado folder. Remember, this is the modified XSA file. If we integrate an XSA file that has the couple of errors we fixed previously, then PetaLinux will throw several errors. Therefore, the most convenient moment to change it is right after we generate it with Vivado. Let's refresh the Win Secure Copy folder so that the project folder appears, and let's double click it. And now we can copy the XSA file in there. For the board support package, we need to go into Real Digital's GitHub repository for the AUP ZU3 board and the open software. And here we'll see PetaLinux base 8 GB board support package. We'll download this file by opening it and then downloading the raw file. And now we'll copy it into the virtual machine in the project folder. At this point, our project folder should just contain two files, the XSA and the BSP files. Then we'll create a project. So we'll copy these two lines. And remove the line break. and hit enter. Here we're telling PetaLinux to create a project using the Zinc MP template and our board support package. Then we install the libtinfo5 package by copying this command and removing the line breaks. Then we install this package and we can remove this Debian file. So if we list the files there, we should see the XSA, the board support package, and the hardware co-design folder. Then we open the hardware software co-design folder and open the PetaLinux configuration. Which will get the hardware description file or the architecture file from the parent folder. Here we can see the different settings of the PetaLinux system. In particular, we'll go into image packaging configuration, hit enter, and disable copy final images to TFTP boot by pressing the spacebar. Then we hit exit, exit, and then yes to save our configuration. Then we'll disable AppArmor so it doesn't interfere with the build process by running these two lines. And we run PetaLinux build. To make it easier to see the effect of having multiple processors within our system, in this case the virtual machine, I'm going to clear the screen and run PetaLinux build. Although it's quite fast, we can see that there are multiple tasks running simultaneously, and this will depend on the number of available processors. Now execute this command: PetaLinux package boot uboot FPGA force. Let's copy it and paste it into our terminal. As you can see, this command created the boot.bin file, which contains these other files, such as the first stage bootloader, the PMU firmware, our bitstream file, uboot, among others. The next step consists of taking the files that were generated by the PetaLinux toolset and packing them into an image that will afterwards write into our micro SD card. To do that, we need to open the images Linux folder. Here we'll see a set of files that were generated by the PetaLinux toolset. Therefore, the next command we need to execute is the one that will pack these files into an image. So in this case, it's the PetaLinux package command. The result of running this command is this WIC image, which we should be able to see once we refresh this folder. And here it is. So once we have it, we can copy it to our folder by downloading it. At this point, we're ready to copy our image into our micro SD card. So we'll run our Win32 disk imager and select our image file. We'll remove the filter to all files and we'll search for the WIC file and open it. We'll select the micro SD card that we plugged into our computer. I recommend that this micro SD card is empty, so this process will take less time. So we click write and then yes. So now that it's complete, we can unplug the micro SD card. To verify that everything is working as it should, we can open PuTTY, load our settings, the ones we previously used. So in my case it's COM3 with a speed of 115,200 and 8 data bits, 1 stop bit, and no parity nor flow control. Our AUP ZU3 board should have the boot switch set to SD because we want to boot from the SD card. We can click open and turn on the board by turning on the USB power switch. The username should be PetaLinux, and we could place any password we want, and we're inside Linux. At this point, we'll move on to creating a C program that will be able to access our programmable logic. Therefore, we return to the guide and move on to section 5, device driver and application development. So the first thing we need to do is run PetaLinux config, but in this case we'll configure the kernel. Here we'll go to device drivers and hit enter. Then we'll go to Userspace I/O drivers. And hit enter. And change the setting for the Userspace I/O platform driver with generic IRQ handling. We do this by clicking space, and we stop when we see the asterisk. Then we hit exit, 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 and then yes to save. And we successfully configured the kernel to run or allow Userspace drivers. So let's clear the screen, and we edit the file systemuser.dtsi. In this file, we'll add the content that has been included in the guide. Removing the unnecessary line breaks that were added by the PDF generator. And then we hit Ctrl X and Y to save. So let's return to the hardware software co-design or the project folder and create an app based on a template. We're calling it half-adder app. This creates a C file that we can open by navigating to the folder called half-adder app. As you can see, it has the basic hello world program, but we're going to override it with something a little bit more complex. So once we delete the file, we'll just paste the code we created from the guide, from page 31 of the guide until page 34. And we can save this code by hitting Ctrl X and then Y. And once again, we just run PetaLinux-build. Now we can package the boot file. The next step is to enter the images Linux folder and execute the command that will generate the image, which will copy into the microSD card. So we'll now copy the WIC file to our project folder in our local computer. So let's open Win32 Disk Imager and load our WIC image file. And load our WIC image file, for which we navigate to the project folder on our computer and deactivate the filter, then select the WIC image and hit write. Yes. Now we can unplug the microSD card and plug it into our board. We'll open PuTTY. Make sure that the cables are connected as before. Load our settings, hit open, and turn on our board. At this point we can run PetaLinux, set a password, and we can run our app. As you can see, these are the results after we run the app in sudo and we insert the password. We have the UIO driver, the size, and then the output from our board. We inserted operand A as 5, operand B as 6, the sum is 11, and we check it with the software calculated sum, which is also 11. In fact, as we see this message, the hardware result matches the software calculation. If we look at the board at this point, we should see LED 0, LED 1, and LED 3 on. So let's try a different number. Let's go with 11 and 23. We get 34. The hardware result matches the calculation, and we should see LED 5 and LED 1 on. So if we, for example, try 65 and 13, this will give us 78, and we should see a bit more LEDs on. In this case we have LED 6, 3, 2, and 1, and we can see on PuTTY that the hardware result matches the software calculation. So this concludes our video series, A Beginner's Guide to Hardware Software Co-Design, building a Linux controlled hardware accelerator on the Zynq UltraScale Plus SoC. To conclude, I'd like to recap what we've done throughout this video series. We began with Vivado and designing a programmable logic circuit that resulted in an Axie4 peripheral. Then we tested it using Vitis on our bare bone hardware. This allowed us to save a lot of time, because if the error we encountered would have appeared after building the Linux distribution and testing it on our board, we would have spent a lot of time and resources and would have had to return to the beginning of the whole process. Then, in this last video, we delved into PetaLinux by using an Azure virtual machine with 20 cores, which certainly accelerated the Linux build process and the micro SD card image generation. And we also saw how to create a C application to control or interact with our programmable logic. I hope you've enjoyed this video series and that it will turn useful in your academic and professional careers. Feel free to reach out to me on LinkedIn, and thanks for watching. So just like in the movies, when they add a brief segment after the whole movie has finished, don't forget to remove or delete your virtual machine, as otherwise you'll incur in unnecessary costs. So to do that, let's return to home, and then we have resource groups. We can enable all the subscriptions, apply, and then we have our co-design resource group. Let's click on it, and then click delete resource group. Apply force delete for selected virtual machines and virtual machine scale sets. We really don't mind at this point, even if we're connected to our virtual machine on our terminal, because it will be deleted and we won't be using it beyond that. So we just have to enter the resource group name, which is co-design. We can write it, paste it here, and hit delete. One of the things I like about Azure is that you can find all the resources related to a specific group, whereas in other platforms you might have to search for them individually. Here you can just open the resource group and delete it, and it will delete all of the contents. So that's it. Thanks for watching.